Hello everyone, my name is Giorgio Orlando and today we'll be discussing the key findings from the paper titled Robust Adaptive Backstepping Control over Native Spaces. Given a plant model in cascaded form in the states X and C, the goal is to design a control law U of T such that if an ideal user-defined control law for C guarantees specific asymptotic performances for the first subsystem governing the X dynamics, then the actual control law U of T will preserve the same ultimate performance on X even when the entire system is considered. Furthermore, this holds despite the presence of both finite and infinite dimensional uncertainties. In particular, the terms highlighted in orange represent unknown parameters for the plant. As previously stated, the model also accounts for functional uncertainties. Specifically, both subsystems are influenced by unknown functions residing in reproducing kernel Hilbert spaces. Unlike prior studies on adaptive control on native spaces, these functions depend on arbitrary observable variables that may be unrelated to the system state and the model dynamics. Consistently with the literature on classical backstepping, we begin by assuming that there exists a continuously differentiable control law alpha such that if the state C were identically equal to such ideal control input, then the state X would be uniformly ultimately bounded with the ultimate bound on X given by the compact set W of X less or equal than K. Next, we present the control law pi for the complete system, encompassing both the X and C dynamics. This law depends on time, system states, and both parametric and non-parametric adaptive gains. The first term is proportional to S, which denotes the error between the ideal control alpha and the state C. The last term is a nonlinear cancellation component that adapts to compensate for functional uncertainties in the C dynamics. In between the parametric adaptive gains theta, pre-multiply an augmented regressor vector, which is modified to incorporate the function h. Such h function resembles what is found in classical backstepping, as it accounts for the error in the energy-like Lyapunov function between alpha and c, and for the total derivative of alpha, which consists of its partial time derivative and its gradient in x post-multiplied by x dot, where the unknown function f is replaced by its non-parametric adaptive gain. Next, we present the adaptive laws. The first two govern the dynamics of the non-parametric gains. Strictly speaking, f hat and g hat rely on infinitely many time-varying coefficients, making direct numerical integration impractical. Later, we will demonstrate how these adaptive laws can be made computationally feasible. Theorem 4.1 captures the main result from this work. In particular, assuming that the user provides a continuously differentiable ideal law alpha for the state C, such that the state X is uniformly ultimately bounded, then the control law pi for the total system with the adaptive laws shown in the previous slide will guarantee boundedness for all the closed-loop signals. Moreover, asymptotic convergence of X and S to the compact set Sk is guaranteed. Interestingly, this directly implies that X will converge to the compact set defined by W of X less or equal than K, ensuring the same ultimate performance on X that the user had in mind when designing the ideal law alpha. Furthermore, if alpha is designed such that X converges asymptotically to the origin, then our control law pi can send both X and S to zero. As mentioned earlier, the adaptive laws must be made practically implementable. One approach is to project the reproducing kernel Hilbert space H onto a finite dimensional approximation space. This will reduce the problem to a finite set of ODEs that can be solved numerically. Increasing n will expand the number of kernels used for approximation, improving accuracy. N represents a trade-off parameter between computational cost and quality of performance. Here is a numerical example where we require a rigid body to follow a desired time-varying orientation in space. We assume that the inertia matrix is unknown, making J the source of parametric uncertainties. Additionally, we consider that the roll channel is influenced by an unknown function of the roll angle and roll angular velocity. Our proposed control law is compared against two other robust backstepping techniques which have been slightly modified to accommodate parametric uncertainties. In the first simulation scenario, the functional uncertainty is modeled using the classical wing rope dynamics. The plot illustrates the error over time between the state omega and the ideal control law alpha. It is evident that the proposed controller outperforms both alternative approaches. The advantage of the proposed approach becomes even more apparent in the tracking error, while maintaining comparable levels of control effort with respect to the least accurate control law. In the next simulation, all gains remain unchanged from the previous scenario. However, this time the functional uncertainty is randomly constructed as a linear combination of Legendre polynomials of increasing order in phi and omega 1, with the maximum order n being user-defined. Since Legendre polynomials are orthogonal, increasing n ensures that the newly introduced uncertainty cannot be captured by any of the previous parametrizations. The bar plot displays the L2 norm of the error with respect to the ideal control law alpha and shows that despite adding orthogonal polynomials to the uncertainty and maintaining the gains unaltered, the proposed controller yields nearly identical performance, even for n equal to 6, where the other controllers fail to stabilize the system. The same conclusions can be drawn from the L2 norm of the tracking error. For large uncertainties, improved performance in terms of control effort is also achieved. This is the end for today. Thank you for watching. For further clarification on theoretical findings, please consult the original paper. Moreover, all codes are available at this link, which you can also find in the video description. For any questions, please email Dr. Laflito at this email address. Finally, we would like to thank our sponsors for funding this project. Thank you again for watching.